Okay, we're working on your final study guide for college algebra, and I'll be starting at number 34 for this segment. This is considered a piecewise graph. You've got f of x, which means y equals, and then we've got three different pieces. And they do not overlap because it's a function, so there's no overlapping here. So each section is defined separately, so there's no overlap. The first section is for x values less than or equal to -1. So we'll be using this definition of f of x, or y equals 2x squared, for the first section of the graph where x values are less than or equal to -1. Here's -1, so it's -1 and less than, so this part of the graph will be, and that's a parabola, so it's going to be some sort of upright parabola times by 2, so a little skinnier than the typical basic one. So expect a little curvature parabola here. And a filled-in dot because it's got a line under it. That's the first section. The second section, y equals 2, is a flat line. It's a horizontal line. And it goes from -1 to 1. So over here at 1, this little section is a flat line through 2. And it should have open circles, unless these graphs run into each other and fills in the circle, which can happen sometimes. But if they don't run into each other, you should see little open circles on each side of this because there's no line under it. Then the third section is a line. This is a linear equation with a slope of 2 and a y-intercept of 1, and it should be for the last segment from 1 over. And it has a line under it, so the dot should be filled in. Again, sometimes these run into each other. We'll have to check that out. What I recommend you do, though, is you make sort of a t-table for each one of these. On the first graph, y equals 2x squared. At its first boundary, it's -1. And then maybe plug in another number like -2, something else in its region over here, and plot some points. So at -1, you got 2 times -1 squared. That multiplies to be 2. So the point -1, 2 is on that graph. And then I just want another point. I know it's a parabola shape out here. Plug in -2. 2 times -2 squared is 2 times 4, or 8. So at -2, it's up 1, 2, 3, 4, 5, 6, 7, 8. So again, it's a parabola shape, something like that. Okay, then for the middle part, y equals 2. Y equals 2 is a horizontal line through 2. Normally, as I said earlier, you would have an open circle at the ends of these, like so, because you don't include its endpoints -1 and 1. But it ran into that graph. You see they share that point. So it looks like it's filled in because of the parabola first graph. Met it there. But anyway, the other side I'm going to leave is an open circle for now. And then do the third section. Y equals 2x plus 1. That's a linear equation, but I'm going to graph it by point plotting. I'm going to start at 1, even though 1 is actually included on this. But even if it wasn't, I would use that as just an idea of whether open or closed circle. So 1 and then 2. Plug that in. Both of those are in that region. That gives me 3. Plug in 2. 2 times 2 plus 1 is 5. So at 1, it's up 1, 2, 3. So it did not fill in that circle. These do not collide. And then 2, 5. Over 2, up 5. And because it's a line, I know just straight stick. And then that's how these three pieces would look on the graph together. Okay, number 35, ask about the topic of symmetry. So I want to review the types of symmetry that we study in this chapter 2 material. We have 3 types of symmetry. We have x-axis symmetry, y-axis, and origin symmetry. For x-axis symmetry, that would be like a sideways parabola. If you could fold it along the x-axis and those curves would meet, it's symmetric with the x-axis. An example of that would be x equals y squared. Those graphs are not functions because the vertical line test would hit it more than once. But anyway, it's still a relation. So x equals y squared, a sideways parabola, would be symmetric with the x-axis. The y-axis would be like our upright parabola. It folds along the y-axis. These curves meet. An example of that would be y equals x squared. The origin symmetry is symmetric with the origin, if you can rotate it 180 degrees, again, origin means rotate 180 degrees and it looks exactly the same. It lies back on top of where it started. It looks the same. So if you can rotate a graph 180 degrees, that's symmetry with the origin. An example of that is this y equals x cubed graph. So what we find is, now that's just kind of a quick overview of it visually, but if it's a graph you're not familiar with, we can also check it algebraically, and we probably should to be sure of the symmetry. The rule for symmetry of each one of these would be the x-axis. To prove its symmetry with the x-axis, if you can change y to negative y, and it makes no difference. It's an equivalent equation. And notice here whether y is positive or negative, it would be the same equation, the same t-table values. That's how you prove it. And then for the y-axis, you change the x to negative x. So whether this is a positive x or a negative x, it would be the same result because the x is squared. And then for the origin, you change both. Change x and y to negative x and negative y, and that shows that it's symmetric. Let me just do that algebra for you here. If this y were negative y and this x were a negative x, a negative cubed would still be negative, unlike the others where they were to even powers. But if it's to an odd power, then I would divide the negative out, and there it is. It's equivalent to what it started as. That would prove that it has origin symmetry. So that's a little deeper into how you can show that. So what we have on number 35 is not necessarily a graph that we're familiar with. It's not one of our basic graphs or one we've focused on a lot. So how do you know it's symmetry? Well, you can use this algebraic way, but a shortcut would be really just look at its exponents. If it has all even powers for the x's, then that means that if you change x to negative x, it wouldn't matter. That's the y-axis symmetry. Well, this has an even power there, but the x there is to the first power. So not all x's would be okay, so it would change it. If all of these were even powers, you'd say yes, it is a y-axis symmetry. Or if they had absolute value signs or something that makes it come out as a positive, a negative to an even, or a negative that's in absolute values. But not so. This x is to the first, so if I change it to a negative x, it's going to change that equation. So it has no y-axis symmetry. Or if it had x-axis symmetry, it'd have a bunch of y's to even powers. It'd be in that way. Not happening, y's to the first. And then for the origin, you need to be able to change x and y to their negatives, and that only happens if they're all odd exponents. So this origin is known as an odd function. If it has origin symmetry, we say it's an odd function because it has to have all odd exponents on the x's and y's for that to happen. So you could check with the algebra and physically do this, the algebra each, but that would be the shorter cut. If they're all even exponents, you can say it's y-axis. If they're all odd exponents, you can say it's origin. If you have a mix of even and odd, fourth power and first power, it has no symmetry, and that's what we have here, no symmetries. If you're using a graphing calculator, you could type that on your graphing calculator and visually look at it also and see if you saw a symmetry. All right, 36. 36, we're graphing some of our basic functions. So you want to be familiar with these shapes to expect. We've seen this one earlier in the study guide. It's the square root function. We've learned that the square root function looks like an arc. It starts at 0, 0, if it's in its standard basic form. Then the shifting rules would say this is grouped with the x. So anything grouped with the x is a left-right horizontal shift, and we do the opposite. So it's a positive 4 or right by 4 shift horizontally. So we're going to move this over 4 places. So 1, 2, 3, 4. That should be the basic look at the graph. If you're in any doubt, you should plot a point on any of these. That's just a powerful way to double check your work. So maybe plug in x. If you try plugging in x as 0, you should get an error reading on your calculator. 0 minus 4 is the square root of negative 4, which would be an imaginary number, or your calculator will say non-real. So it's not plottable for this problem. The first number you can plot is when you plug in 4 for x. It's the first number in the domain. 4 minus 4 would give us the square root of 0, which is 0. So the point 4, 0 should be on your graph. When you look at your choices, there's only one graph that has that point on it. So if you're good with this plugging in and doing your arithmetic, that's a powerful way to solve this. Double check your work. Okay, number 37. We're dealing with another type of basic function that we're familiar with, f of x or y equals. The embedded graph is the y equals x cubed graph, which looks like something like that, swirls around the y-axis. It has been shifted. This is one of those grouped with the x. Remember, if it's grouped with the x, it's a left-right shift, and you do the opposite. So this moves it positive 2 or right by 2 places. When you have a fraction in front, it makes the graph go up slower. It makes it a third of what it normally would have been. The y value becomes a third as tall, so it's shorter. So it widens out the graph usually. You'll see that effect on the graph. So this affects the wideness or the steepness or the slope of the graph. And then the negative flips the graph upside down. Every y equals, every y value over here is the opposite or the negative of what it would be. So the y value is flipped. So it flips upside down, or it flips it about the x-axis. So this graph, envision it flipped and scooted over 2 places and a little wider. So scooted over 2 places and a little bit wider. How much is a little bit? You just need to plot a point to be sure. And I do see on your choices, there's kind of a contest between A and B. So to know for sure, you are going to have to plot a point on this graph to absolutely figure it out. So how do you plot a point? That's a t-table value. You plug in something for x. It looks like if I plugged in x as 0, they're crossing at different places there. But you plug in any number you want. You can plug in as many as you want. I'm going to plug in 0 for x. It'll be negative 1/3, 0 minus 2 cubed. And you can do that on your calculator. But order of operations would say do that first. Then do the exponent next. So that's all negative 8 times negative 1/3, which is positive 8/3, which is about 2 2/3, a little over 2. Well, anyway, you have choices. When you look at these, the first choice at 0 is not even up 1 place. So it's not that. And the other one, you can tell, it's up a little more than 2. So when you look at the 2 graphs, you can definitely tell that graph B is the one that's crossing at the correct spot. And then plot more points as needed. And if there's a choice, two choices that have that, plot another point until you narrow it down. Okay, number 38. Is also using our shifting rules. Y equals negative 1/4, x plus 4 to the 4th minus 3. Now we spent more time probably graphing the embedded graph x squared instead of x to the 4th, but no, y equals x to the 4th looks a whole lot like x squared. It just has a little more of a defined, not really square like I've made it curve a little better, but it's similar to our parabola curve, just a little different base looks like. So it's going to look a lot like the parabola, and then we use our shifting rules. When it's grouped with the x, we move it opposite. So this will be left or back 4 places, a negative 4 move. And then this is a vertical shift. The first one of this series we've seen. A vertical shift is a standalone added or subtracted value, not grouped with the x. It's a standalone. When you have an added or subtracted value, that is a vertical shift, and you do the same sign. We do not change the sign on our vertical shift, so we move it down 3 places. The 1/4 makes it affects its curvature. You might have to plot a point if there's 2 that look they've been shifted correctly, and then it's upside down. All right, do I have time to do that? No, okay, go ahead, turn it